If I can have your attention. Bill. Okay, so before lunch now we are going to have a video. And here she is. You know, her name is Joni Kleypas. And for health reasons, she could not be here today. She is at the National Center for Atmospheric Research in Boulder, Colorado. But she is a Texas gal. She was born in Port Arthur and did a BS, at Lamar University in Beaumont. And she still has, most of her family, in Port Arthur. On top of being, a Texan lady, she's, one of the leaders in coral reef. She is both an ecologist and a geologist, and she has been one of the first, kind of ecologist geologists to realize, kind of the issues of ocean acidification and coral reef. And she is now, among, probably, the top 2 or 3, leaders, in this topic, which is an amazing topic. And I thought it was important in this workshop to at least to have one presentation on trying to talk about the global issues on the coral reef. This is the reefs in Texas, but as we already mentioned in several occasions, kind of the reefs are going through some major issues and stress, and in the future, it's not going to get better. So we're going to show this video. Joni could not, kind of be on a telephone conference with us, but she's watching it, and we wish her, our best for recovery. Okay, let's have the video. Thank you.
Okay, I'm going to just pick up where Dick left off. He gave us a great introduction of the chemical changes that are occurring in the ocean and why we should be concerned about them. And I'm going to give you pretty much a focus on coral reefs. So the title of the talk, Far-Reaching Effects of Ocean Acidification on Coral Reefs, and I say this because we're not just talking about a single organism, we're talking about an entire ecosystem. And so this is the basic outline. Why is this a frontier? And then talking about some of the research challenges that we're facing in terms of ocean acidification and its effects on coral reefs. So 3 basic things under the research challenges. One is, as I mentioned before, this is not just a single organism. It covers the entire ecosystem and a lot of other ecosystems that are associated with coral reefs. There is a problem, as many of you might be aware, that there are many, many stressors on coral reefs right now. And so we're not talking about just ocean acidification. We have to look at it in the context of all these other stressors. And then there's a sense of urgency. We saw how rapidly the chemistry is changing in the oceans. And so that's, to me, probably the biggest challenge of this aspect of climate change. Okay, so for a background, just to give you an idea where reefs occur on the planet. We're not familiar, most of us are not really very familiar with coral reefs and its distribution because we're not all oceanographers in this room, but they are widely distributed. They're in a very important ecosystem. They're called the rainforest of the sea because of their high biodiversity. They support something like 30% of the world's fisheries have life stages which depend on coral reef ecosystems. There's just some astounding numbers of how important this ecosystem is. So just a brief preview for those of you that have never been on a reef or understand what reef ecosystems are like. This is a picture of some coral reefs from satellite view. So these are the large structures that coral reefs form. If you fly down and you look at sort of the ground level, you see that these are big calcium carbonate platforms. Dick mentioned that these are aragonite, primarily aragonite. That is a sort of a soluble form of calcium carbonate. There's 2 major forms, calcite and aragonite. Coral reefs precipitate mostly aragonite. Both of those, calcite and aragonite, are calcium carbonate, but one is more soluble than the other. and aragonite is the more soluble of the two. It's why it's precipitated predominantly in the warmer tropical oceans, because it's easier to precipitate it there. So if we get out and have a look around, it looks like this. If we get in the water, for any of you that have dived on coral reefs, you know that there are these spectacular geologic structures. So coral reefs are amazing. We always think of them for the biology, the fish, the beauty, the vacations, whatever, but it's the geology that makes the ecosystem. It's the rock. So this is the only ecosystem, really, that has such a strong rock component. If you don't have the rock, you don't really have the ecosystem. And so this is a very important aspect of coral reefs. So if you get a little bit closer, we see that that rock is formed by corals and other organisms that secrete this calcium carbonate. And if we get even closer, this is a close-up of the primary builder, which are corals. So these are coral polyps, and underneath those coral polyps is the calcium carbonate skeleton. And this is a schematic of that. So corals are animals. They're similar to anemones. Think of them as upside-down anemones that live colonially and that secrete calcium carbonate skeletons. So here's the calcium carbonate skeleton, and these are the coral polyps. They feed, they sting, they're slimy, they're just like anemones. They grow very fast and they can secrete all this calcium carbonate very, very quickly because they have algae that live symbiotically in their tissues. We call these things zooxanthellae. I didn't put that up there on purpose because we're not supposed to use jargon. These algae are very, very important. This allows corals to live in the deserts of the oceans. So they live, if you think about where they are, they're most commonly in areas which are really, really clear water. That clear water means there's no nutrients, there's very little for anything to live on. But the corals thrive, and it's because they have this nice recycling right within their tissues of nutrients and carbohydrates and everything else by having these algae in their tissue. Okay, this is, I always laugh when I put this slide up because this is one I created for congressmen, so it's fairly simple. There's a lot of things. The more people look at ocean acidification, the more effects that they're finding. So it's not just calcium carbonate secreting organisms. There's a lot of things that can happen. First of all, physiology. So when you change the pH, you're changing the environment in which these organisms live, and you can, there's been studies which have shown that there are changes in respiration rate of the organisms, changes in blood chemistry, and changes in growth rate. That's just a few things. It can also affect reproduction. So maybe because these physiological effects are starving the animal of some of its energetics, then it has a harder time reproducing. If it can also affect the eggs, the state of the eggs, or the success of the larvae. And even if the animal is just fine under acidified ocean conditions and doesn't have any physiological effects at all, it might be affected by the fact that its food supply is affected. And so it's a food chain effect. And I'm sure Vicki will probably talk about this in more detail. But these are just sort of the swath of things that people are looking at in terms of effects of ocean acidification on biology. As Dick mentioned, however, the main thing that we know the most about, particularly in terms of coral reefs, is this effect on the calcium carbonate. It is the main shell-forming material in the ocean. It is what coral reefs are made out of. It is the basis of the ecosystem. And so when we have changes that affect this carbonate ion concentration that he talked about, then we also affect the ability to form these coral reefs. This is a satellite picture of the Florida coral reef tract, and you can see that all of this material in here basically is calcium carbonate. So how do we know this? Just give you a brief background on how we know, that these coral reef organisms are affected by saturation state changes. A lot of the work, some of the best work, because it was done over long periods of time, was in the biosphere 2. And that is this big dome that some of you may recall where they put people in to see if they could live off of their own recycling and resources for a while. Well, that kind of failed. But there were some very successful experiments that were taken over when Columbia University decided to manage this as a climate research center. So in there is a coral reef mesocosm. And just to give you an idea, this is the boat the little person taking water samples. There's a few people here on the ledge, and this is the coral reef mesocosm. And they would change the chemistry of the water consistent with future increases in atmospheric CO2 and measure the rates of skeletal formation as a consequence of those changes. And this is a graph which sort of summarizes many different experiments. And what is remarkable about this is that here's the carbonate ion concentration. This is going from low CO2 to high CO2. These are data that was collected mainly by Chris Langdon. He's done some remarkable work here. And this is the rate of skeletal growth here. So we see that under low CO2 conditions, we have rather high rates of skeletal growth. And as you increase the CO2 conditions, you have much, much lower. It doesn't matter if you raise it back up or go back down. It's this sort of linear relationship. So they're responding directly to that carbonate ion concentration in the ocean. So just for reference, this is the pre-industrial time here. This would be near present day, about 2006. And then by the middle of the century, we see that the change in skeletal growth rate has changed quite dramatically. And if we took it even further, we see that this whole reef system goes into a state from one of net reef accretion or growth to one of net dissolution. So that is about there. But there have been other studies which have gone in the field and trying to measure this and have found that the reef can go into net dissolution much earlier, here or even here, before we reach the middle of the century. So this is, again, threatening the whole basis of the ecosystem. Now, what does it look like? This is a remarkable experiment where some researchers, Fine and Chernoff, put a coral under high CO2 conditions. This is a normal pH. Corals were going under normal pH, and then they subjected them to really low pH, or ocean acidification, ocean acidified conditions. This is about equivalent to 1,200 parts per million CO2 in the atmosphere. What they found is they completely lost their skeletons, but they survived. So they're living just like anemones, but without a skeleton. The good news is that as soon as they returned to the normal conditions, they regrew their skeleton. So these polyps can survive under really low pH conditions. But do you think these anemones, these naked corals, as they call them, can survive in the real world? These are grown in tanks. So the question is how, even if these guys could survive in the real world, they would have to live a very different lifestyle. They'd have to live cryptically. They would no longer be building the calcium carbonate reef. So there's a lot of interesting questions here. You said, what does this mean? How would this affect the reef ecosystem if corals are going to do this in the future? So we have some challenges here. One of the main challenge is, what does the calcium carbonate skeleton do for corals? What is the role? Do we really know that? Well, we know it probably helps in protection. This is the crown of thorns starfish, an amazing predator of corals in the Indo-Pacific. We don't have them in the Caribbean yet, thank God, but they are cause these huge outbreaks in the Pacific, and just, it's unbelievable when you see them going across the reef. It's like a vacuum cleaner. They just go across the corals and just eat the live coral tissue wherever they go. And it's an amazing feat. I mean, not a feat. It's an amazing horror story is what it is when you go down and see this. It's sort of worth seeing. We also know that the skeleton is important for light. So corals have these algae that live in their tissue, which is important for food production and energy for the coral. And so the skeleton itself is white, and it tends to refract light and reflect light in ways that the algae that lives in their tissues can grow more rapidly. It's important for reproduction. So in corals, they are, like I said, animals. They have active reproduction. They produce sperm, they produce eggs, as shown in these two pictures here, but that a lot of them will not become reproductively active until they reach a certain size. So if they're growing more slowly, they're going to reach sexual maturity later, and that's going to change the whole reproductive dynamics in that ecosystem. Calcium carbonate is also very important for reefs. They live on the bottom. They live in really high hydrodynamic regions. There's a lot of wave activity, current activity. So they need to anchor to the substrate, And they also need to get above the bottom because there's a lot of sediment moving around, so it gets them up off the bottom. So this growth rate is really important for getting them into the environment that's favorable for them. And then finally, corals are really competitive for space. So real estate on a reef is very, very expensive. There's a lot of competition. This picture right here shows two corals having a fierce battle with each other. They have these tentacles that go out and they sting each other to say, you know, stay out of my real estate. So there's a lot of amazing battles going on, coral to coral, and also trying to keep the algae away. So when they're not growing fast enough, the algae will come in, the fleshy algae, which can grow more quickly and take over that space. So this function, we really don't know. We haven't measured these functions very well, and so we need to, this is a real challenge to figure out what the real role of skeletons are. We haven't had to think about this before, so this is a new research frontier. Also, what does it mean to slow down the carbonate factory? So this is a picture of an atoll. This is entirely calcium carbonate. And that calcium carbonate is there because the organisms grew and put it there. But as we know, the sea level is going to go up in the future. And if calcium carbonate production goes down, these systems are threatened to be completely underwater. And these systems support a lot of other important ecosystems like mangroves, seagrass beds, and they're important nurseries for a lot of species that live out in the middle of nowhere. Can we lose coral reefs? Well, I'm going to give you a very salient example that says, yes, we can lose them. This is a map of the Galapagos here. So this is and we used to have reefs in these locations. And this is not an ideal location for reefs to grow, but we did have reefs that were growing there before 1982, 1983. In 82, 83, it was a big, whopping El Nino event, which made the waters here very warm, and those corals underwent a phenomenon called coral bleaching. That coral bleaching killed off 95% of the corals. And so the calcium carbonate producers were effectively wiped out during that event. What happened shortly after that was that the reef could no longer compete with the algae. Algae grew on top of the reef, and the sea urchins went berserk. They loved the algae. They started chewing the reef, okay, and the reef disappeared in about 10 years. So there was about 3,000 years worth of reef growth, disappeared in 10 years because we changed the whole dynamics of calcium carbonate production on that reef. Dick showed this, so I think I will skip through it pretty quickly. But as he illustrated, this was a very dramatic change in the saturation state levels on these coral reefs. And one thing that I want to stress is that even if the corals could keep up their calcification rates under these lower saturation state conditions, dissolution would still increase. So this calcium carbonate would still be vulnerable to higher rates of dissolution. So the net reef building would go down. So there are other issues, these multiple stressors, and I could go over a whole laundry list of them, but I will just focus here on some of the climatic change effects. So coral reefs are under assault from many aspects of increasing CO2 in the atmosphere. The top two here are related to the warming of the ocean. So coral bleaching is this phenomenon whereby they lose their algae in their tissues and they're weakened. So this has, so far in the world oceans, we never knew mass coral bleaching events could occur. This is amazing. Every coral on the reef will lose its zooxanthellae, or its algae that it's in its tissue at times. When that happens, the reef becomes very vulnerable. The corals can die if they're stressed enough, or even if they survive, they will be more vulnerable to disease. About probably 10% of the world's reefs have been killed off like this in the last 20 years by the coral bleaching phenomenon alone. Coral disease has wiped out a lot more of those. In the Caribbean, this coral here was a phenomenal coral called Acropora palmata. It's called the elkhorn coral. This coral was everywhere. I remember when I first started diving there, it was everywhere in the Caribbean. It's beautiful, these huge forests. That has been pretty much wiped out by bleaching, hurricanes, and disease in the Caribbean, and it's now on the threatened species list. And so that coral has gone from the most dominant coral in the Caribbean to hard to find. And then on top of that, we have this ocean acidification issue. So I just want to make a quick comparison between the two biggest threats here to coral reefs. This is coral bleaching and ocean acidification. How do we get our hands around this in terms of what kind of research we need to do in the future? So for ocean warming and coral bleaching, this is a very acute problem. Temperature goes up, the corals bleach. It's very, very visible. So we tend to be very passionate about bleaching because we can see it, right? That's a human nature thing. It can kill or weaken the corals. It also has this sort of urgency to it. It can enhance or it can slow calcification rates. Ocean warming can. If it doesn't kill the corals, they might grow faster. But the good news is that with temperature, we know corals can adapt to temperature if given enough time. Apparently, obviously now they are not able to adapt at the current rate of ocean warming, so they're bleaching. But we do have reefs that can grow in much warmer waters if they're given enough time. So that's the good news. If you look at ocean acidification, it is a creeping phenomenon, so there's not always been a sense of urgency because it's like slow. We don't see it happening. It's invisible. We don't see it. It's hard to measure. It doesn't really kill the corals, as we showed in this particular picture. It does slow calcification rate a lot, so it has the threat to the entire ecosystem, and species adaptation is unlikely. So in the short term, this is what everybody's worried about. But even if they make it through this, in the long term, this is probably a bigger threat to the ecosystem as we know it, just because they can adapt and because it's progressive. So this sense of urgency, how do we summarize this sense of urgency on an ecosystem like this? So we can think of it in many different ways. Basically, this is a system of very high uncertainty. We're not exactly sure what's going to happen in the future because we don't understand how these ecosystems respond to such a new aspect of our ocean systems. Ocean acidification just hasn't been seen or thought of. I like to think of it as nutrient. What if we just discovered nitrogen is important to plant growth? How do we begin to tackle something so big? We've just discovered that calcium carbonate saturation state is important to many ecosystems in the ocean. How do we get our hands around this? So here's how we think of it in terms of the urgency and risk. We could say there's no effect. If there's no effect, then just a few of us scientists are going to go extinct. That's what we all want. I think we would all willingly go extinct. Or you could say, well, it's selective species response. We have pretty low ecosystem effects. So we can remove a few species or threaten a few species or slow down calcification rates just a little bit and have low ecosystem effects. We could go up to the bad area where we have reefs beginning to degrade, significant ecosystem response. I still think we are down in this relatively low area here. We could go further and stop reef building. We could reach that threshold where reefs quit growing and begin to erode like they did in the Galapagos. We could have major ecosystem disruption. Or the worst, of course, would be widespread elimination of species and a major extinction event. So we want to avoid this really high-risk area. So what needs to be done? Is what everybody always asks. Well, what do we do about this? Well, this is an interesting thing. We can adapt to climate change. We talk about adaptation all the time. Let's just let CO2 go up, and we can adapt to that. This is an issue that there is no sign of adaptation. So we have to reduce CO2 emissions if we're going to stop ocean acidification. There's no way to reverse that unless we do. In the meantime, we need to concentrate our conservation efforts to where reefs are most likely to succeed. So we should find out which reefs are going to make it under the best case scenario and which reefs we shouldn't put all of our efforts into. We need to buy time with some engineering solutions to help reefs make it through this coral bleaching period. If we can do that for the next 100 years, we can help them a long way. And we need to increase reef resilience by removing all those other stressors that I didn't even talk about, like overfishing, too much tourism, irresponsible coastal development, those sorts of things. And so I will end here by just a quick summary that ocean acidification research is driven by urgent needs. I think that is the biggest challenge, is how rapidly this is happening and how rapidly we need to have the research to meet this challenge and to make policy recommendations. So the main challenge, this is science to save an ecosystem. This is the ecosystem we know the most about. And that entails needing to know multiple scales of research and also multiple levels of support and organization. That includes policy and all of our different research agencies.
Okay, this was maybe a bit, for some of us, a bit too simple, but we have students now here, so I hope you learned something. It was really to make a point that obviously we cannot just be Texas only. Yes, we do. If we are good Texan, as I am, we know Texas is the world, but we need to put the issues of the coral reef into a much more global problem. Okay, so this ends the morning session, and we're going to migrate where the food is. So we have lunch going to be served in the main commons there, and we have an hour and 15 minutes, first 15 minutes to migrate and get our lunch. And I think there's wine left from yesterday, so if you do want a glass of wine, you are welcome, to have one. And we will have, a lecture, probably, about 12:15, at the same time as we finish our lunch. Thank you very much.